Hello everyone, welcome to the course on Fundamental of Electronics Engineering. This is lecture 3 and in this lecture we will see the introduction of operational amplifier. So first of all, what is operational amplifier? So operational amplifier, or in short we can say op-amp is a very high gain differential amplifier whose input impedance is very high and output impedance is very low. So these are the key point, means the input impedance which is very high and the output impedance which is very low. So we can utilize these circuits, these operational amplifiers to design the amplifiers as well as to design the oscillators based on the feedback. So the op-amp is also used as a wideband amplifier or DC amplifier with a very high noise rejection. The basic circuit, the basic symbol of op-amp is this, where we can say that it is having two inputs. One is called as positive terminal, one is negative terminal. So positive we can say it is a non-inverting input, whereas negative input is termed as inverting, whereas it is having only one output. So this is a basic symbol of operational amplifier. Now we'll see the practical IC, which is IC741. The op-amp IC741, which is the 8-pin IC. 8-pin IC. To the left we have 4 pins starting from here, and again to the right we have pin number 5 to pin number 8. So how this pin configuration is represented, we can say here that pin number 2 and pin number 3, they are the inputs, whereas pin number 6 is the output. So pin number 2 basically it is corresponding to the negative terminal, so it is known as inverting input. Positive input is known as non-inverting input. Now the key point is that operational amplifier operates on a dual power supply, means we have plus V and we have minus V at pin number 7 and pin number 4 respectively. Now as we are aware that operational amplifier is having a very high gain, that means if we are not providing any input, then also the operational amplifier is giving certain output. So that output is nothing but a kind of a error which is known as offset. So we have the provision at pin number 1 and pin number 5 to make this offset 0, which is called as offset null. So due to this very high gain, this op-amp is giving certain output, so we have the provision at pin number 1 and pin number 5 to make the output as 0, and pin number 8 is not connected, so we generally left this pin open. So we can write this as NC. Now this is IC741, which is available in a dual inline packaging, DIP, whereas we have dual op-amp which is IC1458 device. So we can clearly see here that there are two op-amps, op-amp 1 and op-amp number 2. But in most of the practical applications we generally use the IC741. Now we'll discuss about the equivalent circuit of the operational amplifier. So what is the equivalent circuit? Means we can say that if we have a op-amp and we are using both the inputs, or if let's say this is VD like this, and AD is known as the differential voltage gain of the amplifier, so the output will be V0 equals to AD multiplied by VD. Whatever is the differential voltage available at the input terminal of the op-amp multiplied by the differential voltage gain will be the output of the op-amp. That means operational amplifier is a voltage control device. So here we are discussing about the equivalent circuit, where we'll be representing the input impedance by Ri, output impedance by R0, and the voltage source which we are representing by AD multiplied by VT. So this is the equivalent circuit of the operational amplifier. Now if we'll make certain assumptions, like if it is an ideal one, so as per the definition, the op-amp is a very high gain differential amplifier. That means as high as possible means the input impedance Ri is infinite and the output impedance is very low, means here the output impedance, which is R0, is 0. So if we will substitute both Ri equal to infinite and R0 equal to 0, so we will be having the equivalent circuit for an ideal op-amp. So we have both the practical equivalent circuit of a practical op-amp as well as the equivalent circuit of a ideal op-amp. Now we'll talk about some basics further for op-amp. Here we can clearly see that we have the feedback. What kind of feedback? Feedback means we are taking some part of the output and we are feeding back at the input side. So that is nothing but feedback. Why we are doing this particular feedback? Because the open loop gain of the operational amplifier is very high and this much huge amount of gain we are not able to utilize properly. So we are taking some part of the output and we are feeding back at the input side. So as we are feeding back at negative terminal, so this kind of feedback is known as negative feedback configuration, which decreases the gain of the amplifier. If we are applying feedback in the positive direction, so that will be a positive feedback and it basically further increases the gain of the amplifier. So we can say that as the gain reduces, the stability of the circuit improves. So the application of negative feedback here is the amplifiers. So we can say that if we are providing negative feedback and we want to analyze this particular circuit, so we have the equivalent circuit Ri, R0 and the voltage gain multiplied by whatever is the input voltage available, which is Vi. We have seen in the previous case. Let's say this is Vi. Now we have R1 and RF. So R1 we are aware that this one was R1 and this one was RF. So we just put this R1 and RF in the equivalent circuit and this will be our final equivalent circuit. Now if we will make some certain assumptions that if Ri equal to infinite and R0 equal to 0, then the equivalent circuit will be reduced to something like this, which is represented in figure C. Now here there is again an important point, then this is AV multiplied by Vi, but if we will change the polarity, because the voltage induced will be positive this side and negative this side. So if we will change the polarity like this, so the value of this voltage source will be minus of AV times of Vi. So again here we have minus AV times of Vi, which is a dependent source. It's a dependent source. That means op-amp is a voltage control device. So we have seen that BJT is a current control device, FET is a voltage control device, and also this op-amp is also a voltage control device. Now we want to calculate Vi, let's say, with respect to two voltages, which is V1 and minus AV times of V1. So how can we calculate Vi? So there is a superposition theorem which says that if a circuit is having two or more than two voltage sources, then the overall response can be obtained due to individual sources. So first of all, let's say we are assuming that V1 is applied and minus of AV multiplied by Vi is represented by short circuit. We will calculate the output as Vi1. So this is a superposition theorem. So Vi1, we can see that how we can calculate Vi1. that Vi1 is nothing but V1 is this voltage V1 get divided in these two resistances. So we will be utilizing the voltage divider rule, which says that V1 multiplied by Rf divided by R1 plus Rf. So we have the first equation, which is V1 multiplied by Rf divided by R1 plus Rf. Now we'll assume the other voltage source, which is minus of AV times of Vi, and by making V1 as 0. So when this is applied, this is 0. Again we need to calculate this Vi, and it is represented by Vi2. So Vi2 will be this voltage multiplied by resistance R1 divided by R1 plus Rf. So this is equation number 2, which is Vi2 R1 multiplied by minus AV times of Vi divided by R1 plus Rf. Now the overall voltage Vi is nothing but Vi1 plus Vi2. So if we will put equation number 1 and 2 in this equation, so it can be represented by this particular equation, let's say equation number 3. So after simplification, means we want to simplify, we want to have this equation in terms of Vi and V1. This is Vi, we are going to move this particular term to the left and will obtain a equation which is Vi equals to Rf divided by Rf plus 1 plus AV times R1 multiplied by V1. Now we'll use the certain approximations in this particular equation, which is that if voltage gain is very high, because we are already aware that operational amplifier is a very high gain differential amplifier, means very high means this AV is very high in comparison with unity 1. So this is nothing but AV. Also AV multiplied by Rf, this quantity is also very high. AV multiplied by R1 is very high in comparison with Rf. So what we can say, we can put both the assumptions, this and this, and we can say that we have equation number 5, which is Vi equals to this equation number 4. This is reduced to equation number 5, which is Rf divided by AV R1 multiplied by V1. So if somehow we have a equation available in terms of V0 and Vi, in terms of V0 and Vi, so clearly we can find out that what is the voltage gain. So the voltage gain for this particular circuit is V0 by Vin and V0 by V1, and this result we need to find out. We have one equation which is in terms of Vi and V1, and the second equation we can have is like this, that V0 equals to minus AV times of Vi. So if we'll put V0 equals to minus AV times of Vi, let's say this is equation number 6. So if we'll put equation number 5 and equation number 6, then we'll be having that V0 by Vin equal to minus of Rf by R1, V1 by Vi. So if Vi will be cancelled with this particular Vi, and we have a result which is V0 by V1 equal to minus Rf by R1. So this result we achieved, this voltage gain we achieved with the help of the conventional technique. This negative sign basically it shows, negative sign shows that there is a phase shift of 180 degree between input and output signal. Means if we have a signal, if we have applied a signal of a sinusoidal signal of this type, then definitely we are getting a signal which is opposite in phase. So this is nothing but V0. And also we need to verify here that AV, the final voltage gain AV equals to minus of Rf divided by R1. So previously we have that the op-amp is having a very huge amount of gain. So this huge amount of gain we are not able to utilize properly. So that means we just want to decrease the gain with the help of feedback. So here we can check that if Rf is of the order of, let's say, some kilo ohms, around 50 kilo ohms, let's say, R1 is also in kilo ohm, so we'll be having a voltage gain AV which is finite. So if this is finite, so definitely we'll be able to utilize this particular amount of voltage gain. Now there is one more concept which is called as virtual ground or virtual short. So the concept of virtual short implies that although the voltage is nearly equal to 0 volt, there is no current through the amplifier input to the ground. Means we can say that there is no current which will be flowing from this negative terminal to the ground. So we can say that the current II is nearly equal to 0. So we have this solid line. It is used to indicate that we may consider that a short circuit is exist and Vi is nearly equal to 0. Means we can say that this these two nodes are nothing but at same potential, because again if they are at same potential, that means there will be no current flowing in these particular nodes. So we can say the current is 0. So this is nothing but the virtual ground or virtual short. So current basically bypass from this particular path, from the feedback resistance Rf, and we can say that no current is entered into the input terminal of op-amp. So the I is equal to 0. So this is the concept of virtual ground. So here we can see that if what is the value of I is nothing but V1 divided by R1. Also, if the same current here, the current is 0, that means all the current is flowing in this particular direction, and I can be written as minus of V0 divided by Rf. So if we'll equate both the equations, so I'll be having again V0 by V1 equals to minus of Rf by R1. So with the help of KVL and with the help of this virtual ground, we'll be able to find out we'll be able to achieve the results for the output voltage or the voltage gain for various types of amplifiers. For example, inverting amplifier, non-inverting amplifier, unity gain, integrator, differentiator, adders, subtractors, and so on. Now what is single-handed input? So as we can see, we have two op-amps. Let's say this is first op-amp and this is second op-amp, and if one terminal is grounded and the other terminal, which is the non-inverting terminal, which is connected at some potential, which is connected by some signal which is Vi, and Vi is a sinusoidal signal. So we are aware that the output will be definitely in phase. The output will be in phase means the phase difference between input and output will be 0 degree phase shift. So this is called as non-inverting output. Whereas if we will see the other case where the input signal is applied at inverting, it is applied at inverting terminal of the op-amp, then we are clear that we achieved a waveform which is opposite in polarity. That means we say that here we have a phase shift of 180 degree. There is a phase shift of 180 degree between input waveform and the output waveform. So this is known as the single-handed input, because we are utilizing only the single we are utilizing only the one input terminal of the op-amp. Now, what is double-ended or differential input? If we can see from this particular circuit that we have VD, which is, let's say this is V2, this is V1, or we have applied a signal, sinusoidal signal in between both the input terminals. So we are utilizing both the terminals of the op-amp, both the input terminals. So that is known as double-ended input or differential input. The signal is applied in a differential manner. So if let's say V2 is high, V1 is less, this is a condition when V2 is greater than V1, means the potential at node V2 is greater than potential at V1. So we'll be having the same phase like this. But if let's say V1 is negative, so definitely we'll be having, if we are applying a signal at only V1 at the negative terminal, so definitely the phase get reversed. So the representation here is Vi1 and Vi2, and what we can say that Vd equals to Vi1 minus of Vi2, and we have the output which is same in phase, right? Or we can say which is having a phase shift of 0 degree. Now we have the differential amplifier. So the differential amplifier is nothing but, we can say, it is a common emitter configurations. Means we have two transistors Q1 and Q2 with the identical properties. Identical properties means the gain, the voltage gain of both the transistors are approximately same. So we are applying, let's say, input at both the common emitter configurations. These are CE configuration. And we are applying inputs Vi1 and Vi2 to the base of the common emitter configuration. And as we have seen in our initial slides that op-amp work on a dual power supply, which is VCC and minus VEE. That means we can say there is a voltage swing will be very high, because if we have a large variation which is from VCC to minus VE, so the voltage swing will be very high, and will be collecting the output which is V01 and V02 at the collector terminal. So if all the properties are same, all the resistance values RC and RC both are same, then we can say that we'll be having the output V0, which we can say V02 difference of V01, like this. So if same polarity signals are applied, if we can say that Vi1 and Vi2, they are applied and they are of same polarity, that means it is called as common mode of operation. And we'll see in our next slides that how this common mode of operation is beneficial for us, because if I'm saying that the noise is introduced from both sides of the input, which is Vi1 and Vi2, then we can say it gets eliminated, because we are taking output in a differential form. So both the noise signals get amplified and they will get subtracted at the output terminals, like V02 difference V01. So this common mode operation is very helpful. It basically eliminates the unwanted noise, like unwanted signals like noise. And if let's say Vi1 and Vi2, they are opposite in phase, means the opposite polarity, so the operation is called as differential mode of operation. So based on this common mode and differential mode, will be seeing one important terminology which is called as CMRR, common mode rejection ratio. Common mode rejection ratio. So what is this common mode rejection ratio? It is a the common mode rejection ratio is the ability of the op-amp to reject the common mode signals and to amplify the opposite polarity signals. So for ideally what we can say, it is or mathematically we can say it is a ratio of differential mode gain to the common mode gain, and ideally we can say the value of CMRR must be as high as possible, means infinite. That means all the common mode signals which we are applying to this differential amplifier or to the operational amplifier, they get eliminated, they get rejected, whereas the opposite polarity signals, they get amplified. So again we can summarize here that the the main feature of the differential amplifier is the very large gain when opposite signals or opposite polarity signals are applied to the inputs, as compared to very small gain resulting from the common mode inputs. So the ratio of this differential gain to the common mode gain is called as common mode rejection, or it is a ratio which is CMRR, common mode rejection ratio. So after this we will be seeing several applications of op-amp, which includes, first is inverting, next we will see is non-inverting, next we will be having adder, subtractor, we will be having integrator, differentiator, and a unity gain amplifier. So now we'll talk about some more about the gain. So as the op-amp is having a very high gain, so they can be connected in an open loop or in a closed loop manner. Closed loop means if we are providing a feedback. So first of all, let me discuss what is open loop. Open loop refers to a configuration where there is no feedback, and closed loop refers to the configuration where we are applying certain feedback. So as we are aware that the open loop gain of the op-amp is very high, it is, let's say, nearly around 10,000 or more than 10,000. So this much huge amount of gain is not beneficial. So we'll go for feedback. Now feedback can be a positive feedback or a negative feedback. So as I have discussed, what is positive feedback, what is negative feedback, means if we are taking some part of the output and we are feeding at the inverting input of the op-amp, so the feedback is known as negative feedback. And if we are feeding the same feedback to the positive terminal of the op-amp, so it is known as positive feedback. Now the applications of negative feedback is amplifiers. Whereas the application of positive feedback is oscillators. Here we can say the gain reduces. The gain reduces. Here we can say gain further increased. And if we are aware that if for any circuit gain reduces, that means we are improving the stability of the circuit. That means if gain reduces, stability increases. Here stability decreases. Stability decreases like this. And further, we have seen several different type of amplifiers like inverting, non-inverting. Similarly, we have different type of oscillators like Wein-Bridge oscillator, RC phase shift oscillator, Claps oscillator, Hartley oscillator, and several others. So in our next lecture, we'll be seeing various applications of op-amp. These are the references. Thank you.